Let's talk more in detail about the security of stream ciphers. So previously we mentioned that the cipher is secure if the pseudo-random number generator really generates random unpredictable bit streams. This is of course the foundation upon which stream cipher security is built upon, but there are a couple of other things to remember. The first is the potential key reuse of the pseudo-random number generated keys, and secondly, the integrity of the messages. Let's first look at key reuse. So stream cipher keys cannot be used more than once. The one-time pad is, by definition, judging from the name, one time and one time only. So let's say we had two cipher texts that were encrypted using the same key. And let's say an attacker gets their hands on both of these cipher texts, and then he calculates what C1 XORed with C2 is. And he will find a result that's going to be roughly the original message 1 XORed with the original message 2, because the keys cancel each other out. Remember that the XOR is an associative operator, so normal arithmetic applies, and if we were to write out this encryption algorithm, C1 XORed with C2, that would be pretty much equal to, well, M1 XORed with the pseudo-random number key and then XORed again with the message 2, apologies for the handwriting, XORed with PRG with the key again. So anyway again, due to the arithmetic for associative operations, you can work this out on a piece of pen, or with a pen and a piece of paper if you want, but the keys will, or the PRGs will cancel each other out in this formula. Then what is worse is that natural languages naturally contain enough redundancy so that you will be able to find, given M1 XORed M2, you will be able to find the original messages M1 and M2 as well. And we know that key reuse is a potential danger when it comes to real-life protocols. That's because real-life protocols that were vulnerable to key reuse have actually existed. As a case in point, the Microsoft point-to-point transfer protocol, a protocol that was used to secure the workstations in the Windows NT era. How this protocol worked is that workstations exchanged messages with a server, but crucially they also used the same key for both incoming and outgoing requests. The obvious takeaway from this is that we need a different key for communications in each direction. Another example of a faulty communications protocol that was susceptible to key reuse attacks. So WEP, or 802.11b, was one of the first security protocols for wireless communications. So that is, WEP used to be one of the ways in which we secured Wi-Fi connections. How WEP worked was that there was a message, the plain text message that was supposed to be, or well, that was encrypted, and it was paired with a checksum for checking the integrity of messaging. And this was XORed together with a random key generated with a pseudo random number generator. And this produced a web packet that contained the ciphertext and an initialization vector, which is here called IV. So the ciphertext was the message and the checksum encrypted with a shared secret key. The initialization vector was a random key, and the shared key K was a long-term key between the client, as in your laptop or your phone, and the whatever was the access point to the internet. The idea behind all of this was to not have to create a new key for each packet, and instead we could use the same long-term key, and we could generate the session keys based on this long-term key using a pseudo-random number generator. How we would do that in practice, the initialization vector changed in each packet. So basically, in the first message we had, the initialization vector was 1, in the second one it was 2, and so on and so on. And the initialization vector was used to initialize the pseudo-random number generator both on the client and on the access point side, so that both could be able to figure out what the current key was at any time. The problem with this design, although it was clever, the initialization vector was only 24 bits long. That means that the same initialization vector value repeated every 16 million packets. And if you have ever used any network sniffing tools, you will see that in a busy network, it's not actually that long a wait. Some 802.11 capable network adapters actually resetted the initialization vector during reboots, so they actually started counting from 1 very, very often, which meant that you didn't actually have to wait for 16 million packets to pass. The biggest problem from an encryption viewpoint was that the random number generator used by web, which was called the RC4 or ARC4, was not the safest, and it was specifically not intended to be used with consecutive keys. It was instead supposed to be used with random keys only. Another example of when key reuse is a problem, let's think about how to encrypt files on a disk. So files are not stored continuously on a disk drive, but they are split into smaller blocks. This is not a problem as such, it's just how files tend to be stored on a file system. What makes it problematic, however, is that if parts of the file change, the change only affects the blocks on disk that contain that particular change. So it's very easy to see which part of the file changed as a result of whatever edit it is that you did to the file. Encrypting the data doesn't help because, again, even if you cannot see what the data is, you will be able to see which part of the file was changed. In summary about reusing keys, well, don't. In network communications, you need to generate a new key for each session, and sometimes even a new key for each communication. And in file encryption, we usually do not use stream ciphers, we use block ciphers instead. Let's then move to the second security consideration, which was the integrity of messaging. So the one-time pad and the stream ciphers do not guarantee the integrity of the messages. Only confidentiality is guaranteed, provided that the keys are one-time use only. So if an attacker intercepts a message and manipulates it somehow it's perfectly possible that your message does not arrive intact. So let's say an attacker gets their hands on a ciphertext. Well, we all know how that ciphertext was formed. It was formed using this formula, the message XORed with a key. What if we generated a sub-permutation key, P, in here, and then append that to the ciphertext by using the same XOR operation? This is a phenomenon that basically shows how changes in a ciphertext can have predictable or predetermined effects in the plaintext. So by modifying the ciphertext, we may be able to modify the plaintext if we know enough properties about the plaintext and about the cipher. Let's take a practical example. Let's say we have an email that has come from Bob. And here on the left we have the plaintext message. And on the right we have the same message, but it's in its encrypted form. So let's say our attacker finds out the content of this first block of the message. The remainder of the message is still unknown to the attacker, but let's say they have guessed that the sender is indeed Bob. So that means that the attacker can guess that the text in the first block will say from : Bob, because that's usually how emails start. So let's think, what do we need to add to the ciphertext with a permutation key to write over the sender's name? To do this, we have to know a little bit about the arithmetic having to do with how data is actually encoded and stored. So if we presume that this text was encoded using the ASCII coding, the plain text message would read something like this. So the letter capital B corresponds with ASCII code 42, lowercase o corresponds with 6F. This is of course a hexadecimal number. Lowercase b corresponds with the number 6.2 in ASCII. Then let's do the same for the piece of text that we would like to write over the original message. So let's say we wanted to replace Bob's name with Eve's. So a capital E corresponds with 45, a V corresponds with 76, and a lowercase e corresponds with 65 in the ASCII table. Then we move on to generating a sub-permutation key using this knowledge. So what we calculate is the Bob's name XORed with Eve's name. If we do this for the first letters of these names, well, we take the first letters B and E, which correspond to 42 and 45 in hexadecimal. And if we do the corresponding XOR with these, we find that the result of B XORed with E is 7. This is the same number in both in decimal and hexadecimal. And then we would simply do the same with O, B, V, and E, XOR them together. And thus we would have our complete sub-permutation key. After all the letters have been XORed and encoded, the sub-permutation key would be 071907. You'll notice that because the operations here for capital B and capital E resulted in 7, the operations for lowercase b and lowercase e is also 07. This is because the ASCII table is somewhat symmetrical, so that's why you get the same result. So this would be in fact the sub-permutation key to write Eve over Bob. So then our attacker's workflow would be here on the right hand side of the screen. So even though our data right here is encrypted, by using this knowledge that we had over the original message, we could generate a sub-permutation key, XOR it with the original message block, and as a result, our ciphertext would no longer contain the original data. It would not say from Bob, but instead it would say from Eve, but of course in an encrypted form. And whoever decrypted the message later on, right here, would find that the plain text message now reads from Eve.